TDRS-L, the newest tracking and data relay satellite, is a workhorse in NASA's ever-expanding space communication network. TDRS-L is the 12th satellite in the series that enables communication to and from Earth. What's new with TDRS-L? Will there be a TDRS-M? Adjust the rabbit ears and find out next on NASA Edge.
We're here live on top of the Vehicle Assembly Building here at the Kennedy Space Center for the TDRS-L launch at Cape Canaveral.
Not the usual sunny weather in Florida, huh?
Yeah, we were sold a bill of goods that said it was going to be balmy down here, but it's a little bit chilly on top of the VAB here tonight.
Hey, but what a great night for launch. We had the TDRS-L spacecraft on Complex 41 getting ready to launch at 9:05 p.m. Eastern Standard Time, and over the next 90 minutes, we're going to be talking all about TDRS and space communications.
And Chris, you had an opportunity to sit down with Badri Yunus earlier today and talk about TDRS.
Badri, we're getting ready for the TDRS-L launch here at Cape Canaveral. How important is this satellite that's launching tonight?
Oh, it's more than important. I look at TDRS with great fascination. TDRS provide the kind of capabilities that are unmatched anywhere. If you look at the combination of all of the network that exists out there, commercial or non-commercial, they cannot come close to the kind of performance that TDRS has provided. Not only in terms of meeting our technical requirement, in terms of reducing the cost and bridging the gaps that existed before. Prior to TDRS, life was close to impossible. We were barely getting 10 to 15% of contact with the spacecraft. So when we needed to have that contact with our mission, primarily human spaceflight, contact may not have existed because of the spatial distribution of the station or other obstruction that may have existed. With TDRS now, with the 100% coverage at any time, 24/7, you can just pick up the phone. We provide better fidelity than that AT&T and all of the other. We approach it 99.999. We don't lose data. We make sure that our missions, get the contact they need, and they meet, their mission requirements.
So I can drop my cell phone coverage and hook onto NASA's, and it'd be even better.
Well, that would be great, but if you can afford our rates.
Now, with TDRS, I understand you've been launching a series of newer TDRS satellites. I think you had the TDRS-K that was launched, and now we're launching TDRS-L, and then you have an M version down the road?
Correct. This is the third generation of the same spacecraft that was conceived in the mid-70s. And then the technology was implemented with the technology of the 80s and the 90s. It has demonstrated its robustness and its viability and its endurance. So we did not change anything on the concept in going from one generation to the other, except with the second generation satellite, we put the processing on board the satellite, but that limited our options in terms of how many users we could support. And also limited our innovation because on the ground we were able to introduce a lot more capabilities and enabling better support of the user than the way we had it in space. So with the third generation, we brought back the processing to the ground. Now we are working on the fourth generation. You probably heard about our demonstration on board LADI. They went around the moon. We were able to, using a 10 centimeter aperture laser, we're able to communicate at 622 megabit per second. So we have been investing in optical communication. We are investing also in state-of-the-art technology, software reconfigurable devices, radios. We are investing also in advanced RF components. Just a few years ago when I was hired, I was given all of these networks and said, Badri, come here to NASA. You have all of these networks to integrate into a single cohesive, unified network. Let's call it the network of networks to cater to all of NASA's future needs, be that human spaceflight or as well as robotic missions. And they didn't give me any money, for that. But thanks to the great team that I have in all of the, within headquarters and within the centers, they worked very hard to identify initiatives that we undertook to generate so much saving and to be able to find money, to fund all of these new capabilities and put in place the kind of capabilities that will return at least 2 order magnitude in terms of performance back to NASA, and to reduce the cost of communicating that bit of data drastically to NASA and to the taxpayer.
Padre, thank you so much for taking the time to talk to us about space communications, and enjoy the launch.
Time. Listen, communication is about information, is about knowledge. You know, without which none of the things we do in, be that exploration or discovering new things, without communicating back, no value.
That's right.
To get a really good idea of just how valuable TDRS is to space communication, Franklin sat down and spoke with the project manager of TDRS-L.
Jeff, as the project manager for the TDRS-K, L, and M satellites, give me a little insight as to what your duties are.
Sure. So our group at Goddard has been around, our project office has been around since about 1973, and we're responsible for fielding the TDRS communications satellites for the agency. So basically our group goes and writes specifications, and then we decide how to do the acquisition. Instead of building it in-house, we've gone out of house, and we help devise a test program to make sure the spacecrafts meet the requirements before they get shipped to the launch site. The primary motivation to do that is, once we launch a spacecraft, it's hard to go back and fix them, and so we've got to make sure we do it right. And then once we launch them, then we perform an on-orbit test program, and then our group turns them over to another organization at Goddard who operates the White Sands complex and operates the spacecraft, and then we're done and we go on to build more spacecraft. That's basically what we do.
Now, with the TDRS-K, L, and M satellites, you had to do some upgrades to the ground station at White Sands. Can you talk a little bit about those changes?
Nothing major, mostly driven by obsolescence, and technology, as we all know, is moving at a pretty rapid pace these days. You probably have, I don't know how many megabytes you have in your home internet connection now. Think back 10, 15 years ago, you probably had a dial-up connection, and you maybe were lucky if you got 300 baud, right? So everything is moving. How many modems have you thrown away at home over the last 10 years?
One a year.
Right. So it's the same with the technology that we use to build spacecraft, and parts that were available back in the late 90s when we built the previous generation just aren't available anymore. So basically, even though the spacecraft of today, the K, L, and M, looks almost exactly like the HIJ series, it's been almost completely redesigned. Likewise, each time we've added a new generation of spacecraft, we've gone and we've made subtle changes to our ground station at White Sands so that we can support all 3 generations in parallel. And that gets complicated because it becomes now the comm system we have at the ground station has to be able to communicate with 3 different types of spacecraft, with 3 different databases, command and telemetry databases, for instance.
So TDRS-L takes off today, and once it's in orbit, it's operating, you have to move on to M.
Right.
When does your work end with the TDRS satellites?
Well, like we said, we launched K about a year ago. There's about a 10-day transfer orbit that we do out of the Boeing Control Center in El Segundo. We'll get to our final geosynchronous orbit, we'll complete deployments, then we'll hand over to our ground system at White Sands, and then from there we'll do our payload on-orbit test program. So for K, for instance, I think our on-orbit test program went through May or June, and that's almost around the clock activity. Then, of course, we got into the reviews and the rehearsals, getting ready for TDRS-L. We'll repeat the same cycle here. We'll launch, but the work doesn't end there. So between now and about a year from April, the work doesn't end for us or Boeing. But on the other side, it's good to have work. And in this business, people tend to take a lot of pride in what they do because we know it's important, and we're fortunate to work with a lot of dedicated people who are just great.
So you're probably about 2.5 years away from being able to go to Disney?
At least a year and a half probably away from being able to say we're going to Disney.
All right, Jeff, thank you very much.
Thank you very much.
All right.
So far throughout this program, we've been talking about the satellite itself, TDRS, space communications, but now let's turn our focus to the operations side. There's a lot that goes on to launching TDRS up into space?
There is. Launch Services Program, we're made up of a lot of engineers and technicians and that specialize in rocketry and spacecraft integration. And part of our job is to select a launch vehicle for our spacecraft customer. That can actually start many years out prior to launch day tonight. So launch day today is actually a culmination of the many years of work by many people.
Is it a case where if I'm a TDRS person and I want to be launched on a rocket and you're helping me, do you help me select the launch vehicle, or is it based on where I want to go? How does that work?
It's a combination of both. You'll fill out what we call a payload or spacecraft questionnaire that goes through our program. And depending on your weight, your size, what orbit you're wanting for your spacecraft, then we will select a launch vehicle out of the fleet that we have. Tonight happens to be an Atlas V vehicle, but we have many other vehicles in our fleet, the Delta II rocket, a Pegasus rocket, which drops from an L-1011 anywhere in the world. And so from the different vehicles we have in the Launch Services Program fleet, we will then size you with what rocket is required to get you your space needs.
So in this particular case, an Atlas V is a pretty big rocket.
The Atlas V is our workhorse.
Right.
It is a pretty big rocket for us, and it's actually our big rocket in the Launch Services Program fleet. It's a very reliable rocket. We've used it many times for NASA missions, and has a long heritage, dating way back to the Mercury days when it launched astronauts, back when it was an Atlas E, Atlas F version.
Now we have some video footage of the Atlas booster arrival at the vertical integration facility. Kind of take us through this and what's going on here.
So the launch vehicle process starts out, as you see here, with booster erection, which this actually occurred earlier in December 13th, 2013. The vehicle rolls into the pad, it's tipped up, lifted into the vertical integration facility onto the mobile launch mount. Here we have the Centaur, which is the second stage. It comes in actually in the opposite direction, rear end first, and then is rotated over on the trailer and then lifted up.
Oh, wow.
As you see here, rotated there, and then lifted up into the vertical integration facility and stacked on top of the first stage. So you have the first stage and the second stage now making up the launch vehicle part of the rocket.
Now in some cases I hear a Centaur being known as an upper stage. Is that the same thing as the second stage?
Same thing, it's an upper stage. Here we see the TDRS spacecraft actually in the payload processing facility, encapsulated in the fairing. Then we start about midnight and we roll out of the payload processing facility, heading down towards the vertical integration facility, which we see here. We've arrived. And of course, the same thing happens with the encapsulated spacecraft. We hook up to the payload fairing with the spacecraft inside. We lift it up on top and mate to the boat tail, which is the top part of the Centaur upper stage, where the guidance section is for the rocket, where all the avionics boxes that control the vehicle.
Is that a sticker for TDRS and NASA, or is that painted on?
That's actually painted on.
Okay.
A gentleman in Harlingen, Texas, that's been his job for many years to paint those on the 4-meter fairings. And he takes a real pride in doing those logos for us.
So if I'm a customer, I don't have to worry about putting all that together. That's part of what you provide for them.
That's correct. We work with the launch services provider, in this case United Launch Alliance, who provides the Atlas V rocket. We have integration engineers, we have launch site integration managers, we have a mission manager, and myself as a vehicle systems engineer. We all make up a mission integration team, and that whole team works with you, the customer, to make sure we integrate you onto the launch vehicle and make sure all the interfaces are proper to get you to space.
It almost feels like I could launch I mean, if I just came to you guys, all the work would be done.
You could. you come to us and we'll take care of you.
Awesome.
Now we had a Facebook question earlier asking how tall is that Atlas V?
Atlas V rocket, the 401 version that we see tonight for TDRS-L, is actually 191.3 feet. For you football fans out there. That's actually about 63 yards if you laid it on its side on the football field. Tonight's a 401, which is a 4-meter fairing, 0 solids, and 1 Centaur engine on an Atlas 500 series. It's the same booster, same upper stage. However, we now go to a 5-meter fairing, which is longer and wider in diameter. So it adds about another 15 to 20 feet to the rocket.
So you've probably seen a dozen of these more than a dozen of these launches. It probably never gets old though.
Actually, I've only seen them on video. So
Oh, this is
really?
great.
Tonight will be my first live
Awesome.
here from the vehicle assembly building. And I'm usually in the launch control room, and we get to see it on the TV. So I'm looking forward to the live launch tonight.
Do you ever push the button, or you?
No, that's not my job.
Well, I'll tell you what we're going to do. We're going to sort of switch focus to the future of space communications, and we're going to be looking at laser communications. So Don, kind of give us an overview again of what lunar laser communication demonstration is all about.
Okay, so LLCD, or the Lunar Laser Communications Demonstration, is NASA's first laser communications demonstration in space that does two-way communications between the moon and the Earth.
Okay. And what is the difference between using a laser communication system as opposed to an RF system?
Laser communications uses laser wavelengths of light, which are 10,000 times shorter in wavelength than radio waves, and that allows you to basically impart 10,000 times more data on a light beam than you can on a radio beam. Also, it allows you to use smaller antennas, which in our case, the antenna is an optical telescope that collects light instead of radio waves. And it also allows you to send less energy to the target that you're communicating with, because the laser beam is so much more narrow than a radio beam. A radio beam is wide, a laser beam is narrow, and so that concentration of that beam allows you to send more power at a distance.
So what were some of the objectives for LLCD in the LADEE mission?
Well, we were hoping to demonstrate broadband from the moon, and we actually did that.
Okay.
We demonstrated 622 megabits per second.
Wow.
Downlinked data from the moon back down to the Earth, our ground station on the Earth. And then also we were able to send data at 20 megabits per second from the Earth up to the moon as well. And by the way, the record before that has only been about 4 kilobits per second. So we beat that by about a factor of 5,000.
Now, I understand that once your systems were turned on, you actually required to signal pretty quickly?
We did, as a matter of fact. So laser communications is used all the time in the Earth. Our internet backbone is powered by these pulsed laser beams that are guided by these optical fibers. So what's the trick? For NASA, we need to be able to take these narrow laser beams and point them where we want them to go and keep them pointed there. So that's the real challenge, and it turns out that we expected we would have to scan the beam around a little bit to find the receiver, so to speak. But I guess all of our calculations worked out so well that when we basically turned things on, everything was pointed in the right place, and it was instantaneous acquisition.
This seemed to be a pretty easy thing to do, but just how difficult was it to acquire that signal in such a short amount of time?
Hitting that target from that distance is the equivalent in golf of hitting a hole-in-one from over 5 miles.
Wow.
So it's a real challenge to point that and keep it there. So there was a lot of thought behind it. There are a lot of things you have to deal with. So because the spot is so small and it's 1 second between the Earth and the moon for the light beam to travel there, if you see the target at this place, you actually have to lead the target, because by the time you send the beam to where you think it is, the moon will have moved.
Right.
And you have to actually lead the target. So it's kind of like how a quarterback has to lead a wide receiver when they throw the ball. You have to see where they're going and put it there. The other thing that we had to overcome as well is motions of the spacecraft itself. So things happen on spacecraft. You have reaction wheels that are turning and parts are moving and things like that, and all that winds up imparting jitter or mechanical motion to the platform. So if I have this really narrow laser beam that I'm trying to point from the moon back to the Earth and the spacecraft is shaking, then my beam is shaking. So we had to design a system that could actually measure the motions of the spacecraft and then cancel them out.
You showed the proof of concept worked. So now is this laser communication system ready for deployment on future spacecraft to maybe visit Mars or the outer planets?
I would say after our 30-day demonstration that we saw nothing that would preclude that from happening. Although I would note that future NASA mission managers that would consider this technology would probably want to see more than 30 days of operating time before they baseline their mission on that. And so the laser communications relay demonstration, which follows us, will actually demonstrate a longer period of operation.
Well, Don, you and your team knocked it out of the park, and congratulations on a successful mission. And it looks like laser communications is here to stay.
Yeah, I hope so. Thank you.
What a great mission that was. We had a chance to, when we did the LADEE live show at Wallop's flight facility, and it was just an awesome job with Don and his team to get the job done and to make that system work.
And that was great, but the work wasn't over there. We have a LCRD.
Laser communication relay demonstration?
Absolutely, and Blair had an opportunity to sit down with Mike Weiss to talk about this program.
Mike, everyone's very excited about the success of LLCD, but you're doing a laser communications relay demonstration. How is it different from what LLC did?
Well, the key word is relay. Relay is really the backbone of today's communication systems. You know, everything we do, whether it's a cell phone or television or spacecraft data, it relies on a relay system. You're going from one point to another point and back to another point, whether it's around the world or from the moon to science station somewhere. It all relies on relay. So what LLCD did was point to point. They went from the moon to the Earth and back. There was no relay involved. There was no networking involved. That's the next step, to go expand these systems so that they are proven to be able to do a relay and the processing and the networking and all the infrastructure that goes with it on the ground. So there's a whole lot to it, and that's what LCRD is going to do.
So is that the final step before we would be able to implement laser communications as a standard technology for spacecraft?
Well, that's the idea. The idea is that this would become an operational system after LCRD is finished. We will have shown that the systems are operational. They can be infused to the users, both the flight terminals and the ground terminals, and anybody who wanted to use optical communication and a relay capability would be able to do that.
It sounds like this is a little bit more complex. How do you prepare for this complexity for your upcoming mission?
Well,
or demonstration, rather, the upcoming demonstration.
Well, we've got something really, really good to build on, and that's LLCD. Right? So we know that the flight system works. We know that you can take an optical terminal and put data through and transmit it. We know the pointing acquisition and tracking works. We know that the ground telescopes work. But all that has to be put together in a relay scenario. So we have to take those two ground telescopes that work so wonderfully on LLCD and make them capable of doing the LCRD mission. So we have to add things like adaptive optics, the modems on the back end, the post-processing. We have to be able to monitor the atmosphere. We have to be able to characterize it, because you have to know how these things perform in order to have an operational system.
This mission is flying not on a NASA satellite, but on a commercial satellite. Tell us about that.
Right, that's a first. It's called hosting. So we have a very, very cooperative contractor, Space Systems Loral. The truth is, they are out in front of us right now. They have worked so hard to make this happen, that they are ready to accommodate our payload on their commercial spacecraft. So things are working very well on the Loral side. We're very pleased with it. And the commercial folks are really looking forward to having optical capability. So it really is a partnership. We're developing technology that they want and they're going to use, and they're helping give us the ride.
TDRS systems currently use RF for communication. Is there ever a possibility in your mind that eventually those will move to laser communication?
Perhaps someday in the future, but right now it's a partnership. Right now it's really about using both. A lot of benefits to using optical, but there still is a place for radio frequency. And so the idea would be to continue to use both until lasers became prevalent and could really be infused, into operational systems as a standalone capability.
It's a beautiful night for a launch.
It is.
Really nice and clear here, looking out over from the VAB out to over the pad. Nice looking rocket too.
And it's your first launch from the roof of the VAB.
That's exactly right. I'm looking forward to that.
5, 4, 3, 2, 1. Main engine ignition and liftoff of the Atlas V with TDRS-L, building our ability to meet the growing future of communications in space.
All right, guys, what do you think?
That was awesome.
That was very awesome. Very cool.
Yeah, I've never seen a launch as clear as it was tonight with the stars in the sky. You could see them all over the place, and to see that Atlas V go up, it was incredible. So we're signing off from the roof of the VAB. You're watching NASA Edge.
An inside and outside look
At all things NASA.